Hi students, we've got some more u-substitution stuff. The only thing that we're doing here is we're taking this to expand it from indefinite to definite integrals. So in the last video we looked at stuff like cosine of 3x dx, and now we're looking at stuff that goes from, like, I don't know, 0 to pi of cosine of 3x dx. As far as the Khan Academy stuff, the definite integrals is the only one that directly applies to this. There are two other ones that I'm putting here because they kind of go with weird antiderivative methods and give you some extra stuff to play with. All right. So what we're going to do is try to make some sense of what's going on here. And I'm going to rewrite my integral a little bit differently in order to begin this process. I'm going to write this as x equals 3 and x equals 2. And then we've got 1 over 2x minus 3. That's a terrible integral symbol. That's okay. dx. The reason that I'm doing this is because we can hopefully see that the stuff that the u is, or the stuff that's inside of this function, we've got this 1 over stuff. And it's that stuff that's the u here. So if I write this as u is equal to 2x minus 3, that's going to make this a little bit easier for us. But let's see what happens. So we've got x equals 3 and x equals 2. When I plug that in, I've got 1 over u, and then I've got dx. We said in the last video that we have to get rid of this dx because it's a different variable. So when we do that, we get du dx is going to be 2, and that means that dx is going to be du over 2. We still have x's as the bounds of our integral, and that's okay-ish. However, it'd be really nice if we had these in terms of u as well. The reason that would be helpful to us is because then we could just plug these things back in. We wouldn't have to convert back to an x thing. So I'm going to find values for u for those, and I'm going to use the equation that we set up up here. So if x equals 3, u is going to be 2 times 3 minus 3, which happens to be 3 as well. If x equals 2, u is going to be 2 times 2 minus 3, which is 1. I like that I wrote x equals 2. Oof. There we go. Now u equals 1. Okay, so now I'm going to finish plugging this stuff in. Instead of x equals 3, we're going to have u equals 3. That's what we just figured out. Instead of x equals 2, we're going to have u equals 1. We have our 1 over u. And instead of dx, we're going to plug in du over 2. Hopefully I realized that 1 over u is the derivative of natural log of stuff. So this is going to be 1/2 natural log of u. And we should do this with absolute value marks because we have to keep the domain of natural log something that works. In this case, we've got 3 and 1. Neither of those are negative. It doesn't actually make a difference. And then I've got to evaluate this at u equals 3 and u equals 1. That gives me 1/2 ln of 3 minus 1/2 ln of 1. You might realize that ln of 1 is 0, so we end up with 1/2 ln of 3, and that's it. To look at this process, the first thing that we did was identify what probably was going to be our u value. We then took the derivative to get our dx, and because we had bounds of integration that were in terms of x, but we switched this to a u problem, we had to set that up in u as well. That's what we did over here. The reason that we did that was that when we then plugged in our values at the end, we didn't have to go back to x, so we didn't have to do an extra substitution step to go backwards in order to make sense of this. All right, so we've got some other ones for us to try. There are 3 beautiful problems here, and all of them are based on using definite integration with u-substitution. The hardest part for most of the students that I work with is definitely the function that's the inside function here. So let's try to make some sense of this. So for the first one, I've got a couple of different functions to choose from. I've got r, I've got square root stuff, I've got 1 minus r squared. The thing that is stuck on the inside of something is the 1 minus r squared. So I'm going to set that equal to u and see if that works. That's going to give us u is equal to 1 minus r squared. Du dr, because we're in r this time, is going to be 0 and then minus 2r. Dr is going to be du over negative 2r. Okay, I then need to look at my bounds. So I've got 1 equals r and 0 equals r. And if I plug in r for, or 1 for r, we get u is equal to 1 minus 1, so 0. And if I plug in 0, we get u is equal to 1 minus 0. All right, so when we do that, we end up getting a new integral going from 1 minus 0 is 0. 1, I like that I wrote that. 1 minus 0 is 1, and 1 minus 1 is 0. So going from 1 to 0, r square root of u times du over negative 2r. Couple things to clean up. The first is that we've got an r and an r, and then I'm going to move this negative divided by negative 2 out front, so we end up with 0 to 1, negative a half, and I'm going to rewrite square root of u as u to the 1/2. Now we are ready to integrate. So we end up with negative a half. This is going to be u to the 3/2 divide by the new power 3/2. Evaluating this at 0 and at 1. 3/2 divided is the same thing as multiplying by 2/3. So 2/3 times negative a half. And then we get u to the 3/2 at 0 and 1. Plugging in 0, we get 0. Plugging in 1, we get 1. Those are nice numbers to work with here. So that's 2/3 times negative a half times 1. Canceling stuff out, we end up with positive a third as our final answer. All right. The second one of these, I'm going to argue, is still pretty reasonable to see what's on the inside, because I've got this weird function, and then it looks like I've got some kind of funky thing inside of a square root on the bottom. So let's take the stuff on the inside of the square root as our u. So u is 4 plus 3 sine x. Du dx is going to be 3 cosine of x, which means that dx is going to be du over 3 cosine of x. The last part of kind of the setup stuff I have to do is to check these two values. So if x equals pi, u equals 4 plus 3 sine of pi. Sine of pi is 0, so u equals 4. If x equals negative pi, by the way, sine of negative pi is going to be the same thing, u is going to be 4 plus 3 times sine of negative pi, which is 0. And we end up with kind of a weird thing, where before we even dive into this, we're going to go from 4 to 4 of cosine x over the square root of u du over 3 cosine of x. There are two things I really want you to notice here. The first is that our cosine x's would cancel out, leaving us with 1 over 3 square roots of u as our function to work with. The second is that we're integrating from 4 to 4. And if we are finding the area under something from the same point to itself, we end up getting 0 as our answer before we do any further math, which is kind of nice. I will do the math out just because I think it's worth talking about here. But that's a nice thing to notice. I'm going to rewrite this as the integral from 4 to 4 of 1/3. I'm going to call this u to the negative 1/2 du. So then when I use the power rule, we go up to 1/2 because negative 1/2 plus 1 is going to be 1/2. So 1/3 u to the 1/2, and then divide by 1/2. And again, we're plugging in 4 and 4, so when we subtract those, we end up back at 0. Kind of a cool problem because of that weird 0 thing. All right, the last thing we've got here is another one where we end up with some tricky things to try to decide what's going on here. I know that I've got both a tangent function and a secant function as part of this. I also know that the derivative of tangent of x is secant squared of x. And the fact that this is the derivative of another part of this is probably a good sign. So let's try setting that equal to u. And when we do that, so u is equal to tangent of x. Du dx is going to be secant squared of x, which means that dx is going to be du over secant squared of x. Okay, we can also change our bounds, and in doing that, if we've got x is equal to 0, and u is tangent of x, tangent of 0 is going to be 0, because that's y over x, and that angle y is 0 and x is 1. And then we've got, if x is negative pi over 4, tangent of negative pi over 4, that's going to be a root 2 over 2, comma negative root 2 over 2 point. When I divide those, I get negative 1 as a value. So we're looking at this as going from negative 1 to 0. We said that this was u secant squared x, and dx is du over secant squared x. Those cancel out, which is really nice because those are really gross. So then if we keep going, we end up with the, and I don't want this to kind of merge there, so I'm going to put a line there. So the integral from negative 1 to 0 of just u du. So that's a power rule for us. It's going to be u squared over 2. And then we're going to evaluate that at 0 or negative 1. 0 squared is going to be 0, and negative 1 squared is going to be 1 over 2. So that gets us negative 1/2 as our answer. This is a really great example of why we do this. So we don't have to plug our tangent stuff back in. You end up with tangent of x squared and then having to plug stuff in after and do some tricky stuff. This is a great example of why we're switching these bounds to make our lives easier.